questions, Connor? We just started a new section, so I'm thinking it's pretty. Not yet. All right. So what I wanted to do today is we did 9. Yeah, we're in chapter 9. 9.1, which was the distance and midpoint of lines, which should be review. And then we started talking about parabolas and properties of parabolas. So what I wanted to start with is just kind of a quick review of some of the terminology that we talked about. And I think that some of the technology, some of the Desmos things actually make things easier to see than what I was trying to do. So I think it's up on here. Yes. Okay. So what this is this is just a Desmos program that somebody came up with that actually kind of lets you visualize what the different pieces of a parabola. So let me take a step back. We're talking all about parabolas. We're going to learn more about parabolas than you want to know. So we're going to talk about parabolas, then circles, then ellipses, and all kinds of things. And there's a couple of properties of parabolas when you go to graph them that we want to talk about. So this is the generic form of a parabola. Now in 9.2, we actually use a simplified version of this. Okay, so we actually used a pared down version of this. But when we get to section 9.6, you'll see that this parabola equation comes back. So what I mean by a simplified version is we actually, when we're dealing with 9.2, all of our parabolas are going to be at the origin. So they're all going to be right here in the center. So this H term right here is 0, and you can see that right there, and the K term is 0. And in fact, if I delete those, there we go. This looks a lot more like those equations that are on our sheet right here, right? X squared equals 4 times P times Y. And then you have X squared equals 4 times P times Y. Okay. So that is, I just wanted to show you that that's that, but we can add an H and a K, and that's just basically shifting our parabola around. So a couple points that I wanted to point out. Let's actually make this positive. There we go. Okay, so this is kind of a review from Monday, but I think it's helpful when we actually have a nice little graph to look at it. So this point here is the vertex of our parabola, right? It's the lowest point or the highest point depending on which way your parabola opens. So this orange dot is our vertex. And in section 9.2, all of our vertexes are going to be at 0, 0. So that makes it nice and easy. We kind of get the simplified case. Okay. Then we have a point up here that is called the focus. So the focus is kind of what the parabola, basically how it kind of curves around our parabola. Okay. And that's been calculated for us using a specific formula. All right. And then down here, this red line is called the directrix. So the directrix basically is the line that's opposite the focus point. So if our focus is 2 units away from our vertex, then our directrix is 2 units in the opposite direction away. Okay. And one of the things that I think is kind of cool to visualize is what happens when your focus point changes. So if I pull my focus point, oh, I shouldn't be playing with it here. There we go. If I pull my focus point closer in, you can see that I get a parabola that's much, much faster growing or tighter into my focus point. And then the directrix also moves in because it's always equidistant from this vertex here. Okay. If I pull my focus point out, way out, okay, my graph's not big enough here, but I pull my focus point way out, right? Then my parabola becomes more and more wide. All right, so I just think that's kind of interesting. The one other thing that I wanted to point out, oh yeah, and then if I'm at 0, then there's nothing. And then if I go negative, if I have a negative focal point or focus point, then I get my parabola that opens down. So I just think that that's interesting to kind of get a feel for what that focus point means. The focus point is a calculation, so we'll do a couple of calculations of that. The other thing that I thought was cool that I wanted to show is in one of these. It's in this one. So this is just this whole chapter that I don't think that our book calls it this, but you can call these conics or conic sections. But this little slide or two I think is helpful. So it has the definition of a parabola. So the parabola is a collection of all the points that are equidistant from the fixed point, the focus, and a line. Okay, so this means that if you pick any point on the parabola, it will be the same distance from the focus as it is from the directrix. So, for example, here, if this is my focus point, right, and I pick this point out here too, if I draw a line, okay, that's 2 units away. And then if I draw, so from my focus to my parabola is 2 units, and from my parabola to my directrix is 1, 2 units. So that's really easy to see that they're equal distance from each other. It's a little harder when you do something like this, right? When you like draw like this to see. But these two distances are also the same as each other. So that's why we have a focus and a directrix that actually helps us to draw a parabola if we don't have a graphing tool. Not that I'm going to make you do that, but that's kind of why we learn what these are. And then this next slide actually calculates it for you. So let's see if I can slow it down. No, it won't let me stop. So what it's showing you is that they have calculated this formula that says the distance from the focus to the parabola is this, and the distance from the directrix to the parabola is this. And so what it's showing you, even though I can't stop the point, I'm trying to make it stop, is that at every single point along the parabola, those two distances are the same. Even though visually it doesn't always look like they're the same, they actually are the same distance. And that's what I was trying to show on Monday, but it's kind of to show it on a board when you're not graphing it perfectly, right? Okay, so then let's do some examples of how to actually find the focus, the directrix, and the axis of symmetry. Oh, I didn't mention the axis of symmetry, but that one's pretty easy. So I think on Monday, did we do number 1? I know we did problem 1. Did we do problem 2? Okay, that's what I thought. All right, so let's do number 3 and number 4 and get this scrolling off the page here. Okay, so what I'm actually going to do is I'm going to snag this. Actually, I'm going to do this. So again, I'm going to let you guys use, use your notes for this section only for the test, because although extremely interesting, I'm not sure that memorizing them is the best use of your time. So, okay, just get this set up. Unless you would like to memorize them, you're more than welcome to memorize. Okay. All right, copy. Oh, it just went to new. There we go. Yeah, I mean, like I said, I think it's helpful, but it's not. It's more helpful to understand what you're doing than to necessarily memorize it. All right, got it. Thank you for copying. You can go away. There we go. All right, so it's kind of all over the place, but I kind of wanted to have my notes here and my problem. And I picked the wrong one to put it next to, but I have y equals -1/4 x squared. So what the first thing that you want to do, and what we're trying to do, I should say, what are we trying to do with these problems, is we're trying to graph the equation and identify the focus, directrix, and axis of symmetry of the parabola. Okay, so the first thing that I'm going to do is to graph my equation. I'll pick one of my many desmoses up here. I could try to kind of force it here, but I'm just going to pretend like I don't have anything, and I'm going to go ahead and graph my equation. Maybe. So just looking at this, if you don't even have a graph up, I know because I have an x squared and my y is not squared, I'm actually looking at one of these two parabolas up here. So I should expect my parabola to look more like the bowl parabolas than one that's opening sideways. And because of my negative, I'm pretty sure it's going to look like this. So it is important to kind of have a gut feel looking at an equation. Okay, what does this look like? And then when you graph it, you can kind of verify. Okay, yep, I got it. I got it. Okay. Maybe. I have too many Desmoses open. Y equals negative 1/4, right? X. Okay, so it is a parabola that opens down. My hint to you was that they're always going to be at 0, 0. So that's good that I'm at 0, 0 here. And I know that I'm going to use the properties that go along with this parabola that opens down. Okay, so basically I need to take this and say, okay, I'm going to use this this key to help me figure out what is my axis of symmetry, what is my vertex, and what is my directrix. Well, for all of these, the axis of symmetry is basically where you can fold your parabola in half. And if we're always through the origin, the axis of symmetry is always going to be right along the y-axis here, right? It's always going to be right there. So the axis of symmetry is always going to be when x equals 0. And that's just because I can fold it in half. So now I need to find what my focus point and my directrix point is. Okay, so if I just go to my equation and I try to match my equation up here, they're close to each other, but I have my 1/4, negative 1/4 is on the wrong side of my equation. Okay, so I have y equals negative 1/4 x squared. And if I want to kind of force my equation to look like this, I want to make it look like x squared equals 4py. Then I need to move this to the other side. So what I'm going to do is I'm going to multiply both sides by negative 4. So I have negative 4y equals negative 4 times negative 1/4 x squared. And I end up with, these guys cancel each other out. And I end up with x squared equals negative 4y. Okay, so now my equation that I'm trying to match and my equation look like each other. And I need to figure out what this value of p is, because p is important because it tells you where my focus and where my directrix are. So I know that this negative 4 has to equal 4p. So 4p equals negative 4, or p equals negative 1. So what that means is for this equation, my focus is at 0, negative 1. Okay, and my directrix, I'm going to abbreviate, my directrix is at y equals negative 1, which is positive 1. Okay, so now if I go back to my original graph, okay, and I kind of scoot over here, my focus is going to be here at negative 1, and my directrix is going to be at positive 1. And if I go to my Desmos focus directrix thing, my focus point is at negative 1, right? And my directrix is at 1. So if I add another line in here, let's see if Desmos will let me. Yeah. If I just add my graph in, my original y equals -1/4 x squared. Oh, I need to make an equal sign here. Okay, so this is red. This is what I just typed in. You can see that it matches up with the focus and the directrix that are listed on there. Voila. Ooh, ooh, ah, right? Super exciting. Yes, super exciting. I know. This is what you wanted to do on Thursday morning. Figure out focus and directrix. Okay, so that is that. One more really quick. We'll just do number 4 since we're here. Number 4, where are you? Is x equals 1/3 y squared. X equals 1/3 y squared. So if I look at that, I have a y squared term. And if I go back to my paper here, I have a y squared term. So because my y is what's squared, I'm pretty sure this, one of these two, is going to be what it looks like. Okay. And it was positive, so since it's positive, it's going to be this guy here. So I'm going to have a right-facing parabola that is not a function, but it is a parabola. Okay. So same process, right? First, I'm going to clear this off so we have some room. There we go. And then I am going to not do that. I'm going to snag the equation. So I'm just going to write it down. This is number 4. So it's x equals 1/3 y squared. Okay. Here's my equation. Y squared equals 4px. Y squared equals 4px. So I need to force this equation to look like the second equation, and I'm going to do that by multiplying both sides by 3. So 3x equals 3 times 1/3 times y squared, or y squared equals 3x. So now I just, since my equations look the same, right, now they look in the same format, I know that this 4p, p is important in finding my focus and my directrix, and I know 4p has to equal 3. 4p has to equal 3, or p equals 3/4. So if I go over here, my focus is going to be at 3/4, 0. 0, that's not a 1, that's 0. And my directrix is going to be at x equals -3/4. And my axis of symmetry is when y equals 0. Because we're just right along the x-axis. Okay, so that is parabolas. Everything you ever wanted to know about parabolas, but didn't even think to ask. Okay. Now I want to actually use Desmos, and I didn't pull this up. I know. Now we're going to talk about circles and ellipses. Okay. So circles are actually not too bad. Ellipses are a little bit more tricky on top of that. But let me pause the screen really fast because there's a, oh, am I sharing my screen with you? Connor, have I been sharing my screen with you this whole time? Oh, you haven't seen it the whole time? Oh, okay. Okay. Oh, you missed the cool Desmo stuff. Sorry about that. I mean, it's exciting, so you're gonna want to go back and watch that for sure. Let's see. Yeah. Oh, yeah, you didn't even see all that. Yeah. So this actually shows you, I'm sorry, completely sorry. It actually shows you that it's always equidistant. Yeah. And here's a nice little tool that actually will graph your ellipse or your ellipse, your parabola for you. So like if you change your focus, then it actually, here, let me delete this other parabola. So this actually shows you when you move your focus in and out, what happens to your parabola. And I probably should use the sliders versus, there we go. Somebody's happy or not happy. Sadness, yes. I'm sorry about that. All right, so okay. Um okay. So there actually is, so I'm skipping ahead a little bit. I'm gonna well, I'll show you what a circle looks like in Desmos, but there's really cool, this thing. All right, I'll show you circles first, and then we'll do ellipses. I just want to make sure I showed you. Okay, so we're going to talk about the definition of what a circle is. Okay, and so actually in Desmos, if we put in, so a circle is defined as x squared plus y squared, you know this one, Connor, equals the radius squared. Okay, so I want a slider for x. Can I add a slider for y? No. Okay, well, oh yeah, we just need a slider for the radius. Okay, so x squared plus y squared equals the radius squared. So for example, if you have a radius of, oh no, I'm doing this wrong. So if you have a radius of 7, I can do this. I can do this. Radius of 7, right? Then you can see that there's your radius of 7 because any point from the center to the outside is 7. And if I drew from here to here, this would also be 7 units. And so this is the standard equation. So what my equation would actually look like would be x squared plus y squared equals 49. Not minus, equals 49. Okay, because it's radius squared. So if your radius is 7, your equation is going to be the square of the equation. So if for example, my radius was 6, then my equation would be x squared plus y squared equals 6 squared, which is 36. Okay, so that's kind of the biggest thing with circles. Desmos makes circles super nice. So before we had Desmos, when you wanted to graph a circle on like your TI calculator, you actually had to graph the top part because think about this equation, x squared plus y squared equals radius squared. In order to graph it, you would have to actually send your x squared to the other side and take the square root, and then you're going to have the positive or negative square root. So if you have a TI calculator you're watching, then you have to actually graph this as y equals the square root of the radius squared minus x squared. X squared. So if you have a TI, this is how you have to graph it. You actually have to graph the top part. So you can see the top part's in black. And you'd have to graph the bottom part because it's plus or minus in red. So Desmos actually does a nice job of graphing circles for you because you don't have to deal with transforming your equation to y equals and then you get 2 parts to it. Back in the old days, you had to graph the top and the bottom of the circle. Now you get to graph it all at once. All right, so that is a circle. Again, the nice thing about it is that all of our circles in 9-3 have a center at the origin. And then we'll talk about moving it around, but that's where they're all going to be for 9-3. So we'll do some problems with that. But the other thing I wanted to show you is to skip a little bit, fast forward a little bit, and talk about 9-4, which is ellipses. And so I'm going to close this because I think it's stressing out my computer to constantly calculate that. So there's a really nice demonstration on Desmos about ellipses, maybe. So that's a circle. An ellipse is looks like a circle, but it's more oval shaped. Here we go. Maybe. Okay, so here is that equation of a circle. Okay, and then it says on line 4, multiply the y squared by a term. I'm just trying to think. I'm trying to do this fast because I didn't prepare this, but I wanted to make sure I showed you. On the line below, you'll find the equation of a circle with a radius of 3. So we just talked about that, right? X squared plus y squared equals 3 squared. On line 4, multiply the y squared term by 3 squared. So we're going to multiply this by 3 squared times y squared. Not up there. Times y squared. Okay, so you can see what happens to a circle when you multiply one of the values, the x squared or the y squared, by a term, and in this case it's 3 squared. Okay, if we multiply by that, then we actually get an ellipse, which is pretty cool. Or if we multiply the x squared term by 3 squared, then we get an ellipse that goes the other way. Actually looks like a cool geometric shape, I think. So these are, it is cool, right? It kind of looks like a 3D circle. So that's what an ellipse is. The thing with the ellipse, and I'm going to kind of skip around here a little bit. Let's see if this is a good one. I might have to re-Google search. Yes, this is what I want. Okay, so these two, this is an ellipse. This particular ellipse is actually a horizontal ellipse because it's kind of fat in the horizontal direction, or wide, I guess, if you don't want to use that word. There's two really important parts, which you can see that are, I wish I could pause this. There's two really important parts that that are part of an ellipse that are these two green points right here. And I'm pretty sure I'm pronouncing this correctly. I'll have to double check. I always forget. But these are actually the foci of an ellipse. So these two green points, it kind of looks like foci. I don't know. But I'm almost 100% it's foci. Are very special because the distance, if you take a string, so this orange thing that's going around that I can't stop, if you take a string and you connect it from the foci to these 2 points, these 2 green points, I'll just call them that, and you basically take a pencil on the end and you draw it around, that's how you can actually form an ellipse. So I've tried to do this activity in class before where I've brought in like tacks and some string, and you try to draw an ellipse, and I might try to draw it in again. I haven't actually yet been very successful. You look online and people draw these ellipses and they look really easy and pretty. But basically, if you have these two foci points and then you attach a string to it, and imagine this is your pencil, and you just take your pencil and you kind of wrap around, then that's how we actually ellipse. So that's why these 2 points are important, and we'll spend some time figuring out how to calculate where those 2 points are. And there's a couple other things that go with that. But basically, if you look here, the distance, if this would stop, just stop for a second. Oh, I know what I'll do. I'm going to print screen it. There. There we go. I stopped it for a second. Okay. So if you look here, right, this point along here, the distance from this green focus point, from the foci, so the distance from this green point to my black point is 2, and then the next distance is basically 8. So those added together are 10. So the distance between my two focus points is the same for every ellipse. So now if I escape and I hit print screen at some other random spot, now, okay, then if I look here, the distance from this focus point to my ellipse is about 3.5, and from the ellipse to this focus point is about 6.5, and if I add them together, I get 10. So that's kind of an important part with ellipses, is how we draw the ellipses, that this distance from the ellipse to each of the focus points is always a constant number. It doesn't always equal 10. It could equal, 100 or something like that, but it's always equal to each other. And I think that's way easier to look at on here. All right, so what if I change this to 12? Oh, right, it won't let me. It won't let me break the program. All right, so I can't change it, but that just kind of shows you how an ellipse is formed versus a circle in this relationship. And it's way easier for me to show you on Desmos than for me to try to draw it. Okay, so there's some cool little things that you can do with that. You can draw a little pumpkin and all kinds of fun stuff with that. Okay, so back to, I just wanted to show you that, so when we get to parabolas, I'll try to sketch it on the board, but it's going to be much easier to look at here. So back to circles. Circles are actually pretty easy. So this is a nice little easy 9.3 section. So circles, we take out the whole fact that we've stretched either side of our circle, right? And we just go back to this always x squared plus y squared equals radius squared. Always kind of works. Pretty easy peasy. The hardest part is transforming your equation. Okay, so if I go back to my notes for 9.3, and I have, it says graph the equation, identify the radius of the circle. So all of these in this section, again, have a origin at 0. We haven't shifted our graphs at all anywhere. We have x squared plus y squared equals 9 is the equation that we want to graph. We know it's going to be a circle. All right, and it looks a whole lot like x squared plus y squared equals radius squared. So just based off of this, I know the equation of a circle is x squared plus y squared equals radius squared. So I know that my radius squared is going to equal 9. And if I want to find what the radius is, I would take the square root of both sides, and I know my radius equals 3. So that's pretty much it. Graph the equation, identify the radius of the circle. So just to double check, if I go back to my ellipses here, let's get rid of all this stuff. Okay. Yeah, we'll leave that too. Okay, so my equation was x squared plus y squared equals 9. Okay. And I said that I think that means that my radius equals 3. And look at that, those two match up, so I did a good job. Yay. Yay, us, right? Again, pretty easy section when it comes to that. The next one, try to trick you slightly. Y squared equals negative x squared plus 49. Okay, so I know that my equation of a circle always looks like this. So if I add x squared to both sides, I get y squared plus x squared equals 49. All right, 49 is my radius squared. So my radius is going to be 7. Okay. And then number 3 is like a little bit trickier, right? But not that tricky. we have x squared minus 18 equals negative y squared. So the first thing I need to do is just put this into the form of a circle. Okay, so I'm gonna take this up here. X squared minus 18 equals negative y squared. So I'm going to add 18 to both sides, and I'm going to add y squared to both sides. Yeah, y squared to both sides. That's kind of messy. All right, so what I basically end up is with x squared plus y squared equals 18. So that means my radius squared equals 18, or my radius equals the square root of 18. So this isn't going to be a perfect radius, but if I evaluate what the square root of 18 is, that's about 4.24. So if I go graph my original equation here, I get x squared minus 18 equals y squared. No, that's coming up next. Negative y squared. There we go. All right. And so I said my radius is about 4.24, which is pretty close. Or I said it's equal to the square root of 18. Not the square root of that, square root of 18. So now you can see that the graphs are right on top of each other. So circles are pretty easy, right? We have one more problem there that I'll save for class on Monday, where we actually use the distance formula plus this formula. But I think that's probably a good spot to stop. So, make sense? Circles seem pretty easy. Yeah. All right. Good deal. Yeah, they are. There's no giant trick to them. That's just a circle. So, all right. Sounds good. Thanks for coming. I'll talk to you later. Bye.